and in a way of introduction. I am not a chemistry man, not a crystallographer. I am not a mathematician, and I am not in mathematical combinatorics. So it's quite a courage to enter into such an era about which deals my present lecture. A combined research platform, לא, תחזיר, תחזיר רגע, a combined research platform of structural morphology, dealing with the ordered 3D space. My story with structural morphology, when I was assistant, I started this topic, and some believe I gave the name of structural topology for the first time. And from that time, it is carried out and distributed around the globe. Dealing with the ordered 3D space. I will read some of the text presented here. The architecture of the human habitat and the whole domain of physical space structures is mostly concerned with few basic three-dimensional spatial features and their diverse interrelations. Networks, the first, space lattices, arrays of interconnected vertices representing physical or imaginary abstract entities that might stretch to infinity. For me, an array, a group of people, every head is a vertex of a network. Polyhedral finite or infinite volumetric solids. Yeah, we are living with it from the time of our birth, with plane or curved hyperbolical facets that might be associated with compact close packing of 3D space, and space dividing partitions, finite or infinite, between any conceivable spatial entities. The structure and morphology of any configuration in 3D space might be represented by complementary association of the above described features. It follows up that every 3D network is associated with specific polyhedral close packing. The cubic network is associated with a close packing of cubes. Every 3D network has a construct dual network. If you take the vertices, the centroids of the cubes compactly packed and join them together, you receive another cubic network. The two associated dual networks, one inside the other, are genetically related to the centroids of the solids that provide for the structure of their dual feature. Every dual network's pair is associated with a hyperbolically extending 3D space partition, subdividing the space between the two. This surface is a partition subdividing between two dual cubic networks. Next. Here you see a uniform network stretching, which could be stretched to infinity. All the vertices are identical, all the edges are identical, At every vertex, you have 7 edges meet together in the same manner. Every vertex is same symmetrical feature. Here on the lower part, down, it's me, more than 50 years ago. Some of my students around, 2 of them already passed away. Next.
And your son.
Another surface is the same surface, and it was sewn from old sleeping sheets by students, American students in University of South Carolina, yeah, South, yeah, and it's a very intricate surface, but to provide it is based on a very simple, straight knowledge. Now, here you see a octatras, the blue network. Its dual network is the packing of rhombic dodecahedra. So the rhombic dodecahedron and its compact space packing provides for 1, and 2 solids, tetrahedra and octahedra, their compact space packing provides for the 2nd. And rhombic dodecahedra, because of these 2, have 2 types of vertices, while this network has only 1 type of vertices, because all the rhombic dodecahedra are alike. And in between, you have the hyperbolic continuous stretching to infinity partition. Next. Another, this is, I call it a quintuplet. You have 2 dual networks, 2 types of close packing solids, and a partition in between 5 complementary features. Next. The combination of the 2 dual networks, the 2 associated polyhedral close packing configuration modes, and the associated 3D space partition between the dual network pairs represent 5 spatial features deeply associated and interconnected with one another that provide for a critical characteristic of 3D space only, to be termed by me the quintuplet phenomenology of 3D space. It should be stressed that determination of one feature of the 5 provides for the determination of the other complementary 4. And when periodic in nature, all the 5 constituents of the quintuplet share in same symmetry regime. Next. Level of the quintuplet constituents periodicity symmetry plays a defining role in their categorization as 3D spatial phenomena, ranging from the most accidental to the most symmetric uniform. Next. One such network, trivalent, with 3 edges joining in every vertex, trivalent uniform network stretching to infinity. Its dual network is again the same network, which means it's a self-dual network. And the solids generated inside are these, with 3 faces, only each face decagonal, and this solid by itself provides for a compact space packing. Sorry, Euclid didn't knew about this possibility. Next. An important category is that of the translation networks, controlled by translation symmetries that determine the shape of their translation units. Next. Some of the translation networks may be associated with uniform equivertex edge networks. Some symmetry characteristics may lead to uniform networks self-duality. And now we will consider self-duality. This is the solid. Since the two networks separated by this surface are the same, this surface includes symmetry elements that take one network into its dual network. These symmetry elements are of a twofold kind, either a reflective twofold rotation symmetries or points of reflection on the surface. In this case, on this periodic surface of the unit, they have 8 inversion points and 24 twofold axes of rotation symmetry. Next, yeah. Next. Every vertex of a uniform 3D network is a centroid of a self-packing volumetric polyhedral solid. That was already told before. The morphological study of crystals of various symmetry profiles showed that they could be referred to 7 different sets of crystallographic modes, each set possessing characteristic symmetry structure. Every basic inorganic chemistry text is stressing the point that of crystallography 3D imagery domain is controlled by 14 Bravais lattices. Bravais, whom we met before, who in 1844 published his main work, his translation networks. 14 Bravais lattices, including the triclinic, monoclinic, orthorhombic, trigonal, hexagonal, and cubic isometric, all representing crystal symmetry systems, all featuring 7 translation network types. And here a little surprise. 13 of the Bravais lattices, except that of the hexagonal, are self-dual, which means the 2 dual networks represented by that symmetry, reflection symmetry, translation symmetry, Bravais lattices, 13 of them have surfaces subdividing between the dual networks. Here you can see the monoclinic, triclinic, monoclinic, orthorhombic, tetragonal, trigonal, hexagonal, and the cubic. Each of these represents a point group. Next. And here I come to Fyodorov. In 1885 to 94, Yevgraf Stepanovich Fyodorov, followed by Schonflis and Barlow, have independently proclaimed that all of 3D symmetry space groups consistent with the 14 Bravais translation lattices reported in 1848 were accounted, and their number is reaching to 230. Next. Knowledge of the Bravais lattice alone is insufficient to reconstruct a crystal structure. We need to specify the internal symmetry of the unit cell, its point group, along with the lattice. This combination is known as the 3D symmetry space groups. And as Fyodorov proclaimed, 230 symmetry space groups. Symmetry characteristics of the uniform networks of 3D space. We start with the symmetry systems, and it is split. In fact, symmetry system, 7 symmetry systems split into 32 symmetry point groups that are accounted by 230 symmetry space groups and infinite number of symmetry elements. Many of them are not associated in this play. Next. Yeah. So according to Fyodorov, 7 symmetry systems, 32 symmetry point groups, 230 symmetry space groups, and symmetry elements. Next. The number of the 230 3D symmetry space groups was attained after a meticulous combinatoric process of all the symmetry elements which were considered relevant and associated with the 14 Bravais lattices. Every symmetry point group is characterized by an associated order value representing the number of fundamental domains within a translation unit of a related Bravais lattice. Fundamental domains. Next, the number of fundamental domains of a translation unit of a given point group structure represented by a certain order value, and the maximum number of vertex figures in a translation unit of an associated uniform network are the same. Within every fundamental domain, we can push and maintain only one vertex, different from all other possible point locations within that domain. And so uniform network with its uniform vertices, one vertex per one fundamental domain. Next. According to Fyodorov and al., the highest order value of the cubic symmetry system is reaching to 48, implying that a cubic symmetry system related uniform network with the number of its vertices per one translation unit reaching beyond 48 is a theoretical impossibility. Only 48. Next. Cubic Bravais lattice and symmetry system. Maximal order value is 48. It evokes the Fermi surfaces, but I will not go into that. But here you see on this surface 8 inversion points and 24 twofold rotation symmetry axes. Every symmetry axis subdivides a fundamental domain into 2, enabling 2 identical vertices per one fundamental domain, which means the fundamental domains are half of those envisaged by Fyodorov. And the number of fundamental domains within this subdivided by this surface is rising to 96. Next. That you can see through all the symmetry system except that of the hexagonal. so the other 6, the number of symmetry elements which were missed by Fyodorov and his colleagues amounts to 80 symmetry elements that didn't participate in the combinatorics that defined that the number of symmetry space groups is 230. Next. As a result of the self-duality of certain Bravais lattices and the generated twofold symmetry elements, inversion points, and twofold rotation axes, the order values of the associated point groups have doubled. Next. And here you see a network which belongs to the cubic symmetry system. And here you see a translation unit. And with this translation unit, you can see 96 identical vertices, not 48. This network was escaped the attention of all our colleagues from Euclid up. Next. Another network. To this day, I went through and constructed more than 700 uniform network types. And few dozens went beyond the upper order limit. It is a surprising fact that there are already few uniform networks of the cubic symmetry system with 96 vertex figures per one translation unit, implying that the exhaustive enumeration of 3D symmetry space groups is not complete. 80 symmetry elements associated with certain self-dual Bravais lattices, with the exclusion of the hexagonal one, non-self-dual lattice, were not considered in the symmetry elements combinatorics. And here I cut the way short. According to the author's analysis and in consistency with the 14 Bravais lattices, the numbers should be as follows. Symmetry 7 systems, that remains as it was. But point groups, instead of 32, there are 74 symmetry point groups. And symmetry space groups, it went up to 562. And the number of symmetry elements is n, as previously thought to be, plus 80, which were escaped the attention of Fyodorov, resulting from the Bravais lattice self-duality. Next. The combined research platform is aiming at exhaustive enumeration of the most symmetrically uniform morphology features concerning the following. "3D symmetry space groups." Sorry, in order to continue, we have first to accomplish the 3D symmetry exhaustive search, because that's the only way to prove that the other exhaustive efforts are complete. Second, uniform 3D space networks. I have today more than 700 already solutions, and I believe it can go high, maybe twice as that, to 1,000 and so on network. But the way is still long. Self-packing 3D space polyhedra. It's a very interesting point. We are packing nearly everything from bottles to our apartments in buildings, and self-packing is a very supportive tool for the packing technologies. Hyperbolic partitions between self-dual network pairs. Self-dual network pairs. Every self-dual network pair, and there are many dozens, between any two such, there is a beautiful one specific surface. Hyperbolic partitions between uniform dual network pairs. Here, the field is also very widely open. Yeah. Geometrical topological solution and exhaustive enumeration of the above might contribute considerably to our present day perception and understanding of 3D space related structural morphology at large, crystallography included. Thank you very much.
Wow.
Thank you very much, Michael. Thank you. No, we are open for discussion. Any question for to Michael? Vera has a question.
Yeah.
Vera, please.
I have too many questions to ask here,
For
so
We
I
have
will
to
just
3 hours sitting together.
yes, or more, with a computer at hand and some models. As I said, I have many questions, and I would like to know more your research and these conclusions and how you got them. But it seems to me that you are first including the notion of saddle polyhedra, in which, for instance, Peter John Pierce has done research on that. You know his book, certainly, right? You know this book from Peter John Pierce?
I don't think, if you will send me one, it will be a great present.
I have it only in printed form. It is very, very good. It was written in 1970 something too or so, and he has done an exhaustive research on saddle
What's his
polyhedra.
name? What's the name of the
Peter John Pierce is an American author.
Yeah.
Pierce, I think
Yeah,
you know
okay.
it.
Yeah, I think you do. It will be strange if you didn't.
Peter Pierce.
Okay, so I believe that first of all, I'm not sure if the surfaces that you have done are hyperbolic. Some analysis will have to be accomplished to determine if they are hyperbolic or not.
I dealt with these surfaces more than 50 years ago.
Mhm.
My first interest in them was looking at them as minimal surfaces. But the symmetries are included. Within the surfaces, you see, you have quadrangles.
Mhm.
These are symmetry elements. Inside, there is a slight, very slight difference between the minimal surface and the hyperbolic, parabolic surface. Yeah, the difference, but in order to construct this and produce this surface, I preferred the hyperbolical paraboloids instead of minimal surfaces. They were easier to construct.
Yes, but
Michael and Vera, sorry for interrupting you. Michael,
Yes.
please stop sharing the screen. And in this case, you will see better the book that was presented by Vera, and we can see your models, the beautiful model which was in your hand.
Yeah.
So stop sharing the screen.
Okay.
Good. And now,
Okay.
Michael?
Well, those are not part of that surface is probably an hyperbolic paraboloid, but they are not all of them, and depending on the structure, they are not hyperbolic paraboloids. Euclid could have never devised that because he was not conceiving saddle polyhedra. That simple, right?
Again, I'm sorry, I have these little devices in the,
Oh, sorry.
and one of them is missing. Yeah.
So we really have to speak in person one day.
Face to face, okay.
Yes.
Maybe the Porto Congress would be a good possibility.
Can I just add something? You have shown a drawing that resembled this form, right?
Yeah.
This is a rhomic truncated cobactohedron that you have done from the surface, but that is an extension of this one, the cobactohedron.
For sure.
When Fyodorov was considering his theory, he was looking at this one because it is the least possible
The
shape,
order of this
polyhedral
one
shape.
is lower than the order of the other one.
But this is more. This is a how do you say it? An optimal solution for the problem. When you enlarge the possibilities as this, and this is possible to. You model this from this one by expansion, as Alicia Boulstott has done. So this is possible.
Same symmetry system, the cubic symmetry system.
Mhm.
Yeah. But
Yes.
the cubic symmetry system consists of few point.
You are mentioning the cubic lattices at first.
Yeah.
You began with the cubic lattice, and you have done from the body-centered cubic lattice.
Yeah. But still, according to Fyodorov, cubic point groups have networks that refer to order 12, 24, 48. I think 1, 12, 3, 24, and 1, 48. 48 is the most developed. Yeah.
Mhm. Mhm.
Some solids have only 12 identical vertices. Yeah.
Well, the thing is that, and I do not want to jump into a technical discussion because it is not interesting for everybody, but we will speak about this later. But when you enlarge the possibilities, more things happen. In Porto, yes, of course, I hope. But when you enlarge the possibilities, when you consider, for instance, if you consider that polygons may have curved edges, as I know you do, you get other results that are not the same. The premises are different, so you get other results. So probably this is what is happening here, and this requires more analysis and research. But again, thank you for your presentation. It was very interesting.
Thank you.
Thank you. Thank you. Any specific question to Michael? Yes.
Look at that. This is one of the surfaces. In fact, it's the same surface as this.
Yes, yes, yes. But they are not hyperbolic surfaces for sure.
Cut along the twofold axis of symmetry.
Mhm.
Yeah.
May
And
I ask? Yes.
I
Go
want
ahead.
to make a little remark. Ed Goranson, I expect us to discuss this issue because this program might interest you.
Well, I've always been interested in this from not from so much the crystallography end, but as characterizations of networks, right?
Yeah.
Because these are what we're talking about are spatial representations of networks, and networks are a fundamental topic of the kind of computer research that I'm engaged in. So I definitely am planning on pursuing this with you in some way.
Thank you very much.
So,
me
thank you very
just
much.
add that-
Vera, yes.
Just to say, sorry, Eugenie, just to say something. I sent in chat, by chat, the link to the book that I mentioned, okay?
Thank you.
Yeah.
Any more questions? Yes, Eugene, please. Eugene.
Yes. Thank you very much, Michael. As always, it's very interesting, and I really appreciate a huge job which is behind your talk. My question is, do you know that in material science of carbon nanomaterials, there is a material which is called Schwarzwald, Schwarzite. And this is exactly materials with the network you show the model with this negative, you discuss it with Vera about it. And I think it's a lot of knowledge can be used from this kind of, a lot of papers about these materials and structure and whatever.
Eugene,
Yeah.
you're my neighbor.
Yes.
And Haifa is very close to Beersheba.
We have
So
a deal. I will come to you. Yes.
please be kind and go to the far north on the Carmel Mountain.
Yes, exactly. Deal. I promise you. We'll
This
discuss
is the
it.
importance of our conference, that immediately 2 meetings were organized already. So it is very good. Yeah, so thank you very much. I
And the
don't see.
location for the next Congress suggested, don't forget that.
Yes, yes, yes. If there are no more specific questions to Michael, of course, there are many, many questions to Michael, which we should discuss later.